Welcome to the lesson on particle diagrams. Many of the slides in this presentation are courtesy of Summit Learning. Just wanted to point that out. In this presentation, we will be discussing particle diagrams and how they are used to explain characteristics of gases. Those characteristics being temperature, pressure, mass, and volume. Let's start off talking about particle diagrams and what are they and why they are important. Beginning with why they are important. It is very difficult to see an atom because they're so tiny and they're so small. And so because we cannot see them, we need to develop some way to visualize or see them, in quotes, so we can explain what's happening and why it's happening. And that's what particle diagrams are used for. So what they do is, in a particle diagram, it shows the particles, which are atoms or molecules, in a substance. And these are usually depicted as little dots or circles. Now, in this unit, we're focusing on one of the phases. You know that there are three phases of matter: solid, liquids, and gases, and we're going to focus on gases. And so it's important to note that all of the examples in this PowerPoint are of gases. Okay, let's see if you can pick out the particle diagram of a gas, given what you know. So which of the following images accurately depicts the particle diagram of CH4 or methane gas? Take a moment to pause and make your decision. Okay, the correct answer is E. So let's figure out why that's the correct answer and the other ones are not. First of all, particle diagrams, remember, they depict atoms or molecules as dots, and that's what we see here. So each of these dots would represent CH4 or methane. The other thing is, since it's a gas, remember gases spread out and they occupy the entire container, and that's what you see happening here. So all of the particles are all spread out. Let's look at some of the other non-examples. So A, as you can recall from last unit, is a model of methane. This is something that we built in class using the model kit. Here we have the Lewis dot structure, that's B. C is a particle diagram of a liquid. Notice how all of the particles are at the bottom, and they're not regularly shaped, so there's a little bit of space in between them, but it can move around and flow over one another. And here is of a solid where the particles, again, they're all at a bottom, and notice that the solid has a fixed shape, so whatever the shape of the solid is, that stays the same, and the particles are more regularly shaped. Okay, so now let's get into what a particle diagram can show you and how it can be used to explain things like mass, volume, pressure, temperature, etc. Let's begin with mass. So what is mass? It's important to know what that is. That's a measure of how much stuff there is, and the more particles you have, the more massive your sample is. So if we look at the example here, we have an Erlenmeyer flask, and it contains 1, 2, 3, 4 particles. And the second Erlenmeyer flask contains more than 4 particles. If you count them up, we have 2, 4, 6, 8 particles, right? So this one has more particles, and therefore it has a bigger mass. Now, to be clear, we're assuming that both of the containers contain the same type of particles, like both either contain all helium atoms or both contain all hydrogen molecules. If they didn't have the same type of particles in each flask, we couldn't make that comparison about the mass. But let's say that they all had just helium atoms. Because this has 4 and this one has 8, we know that this one has a bigger mass because there's more particles in it. The second characteristic we're going to look at is volume. So volume is just a measure of how much space a particle takes up. Now recall with a gas, the volume of a gas is the same as the volume of the container because gases don't have a fixed volume. So if you take a sample of gas from a 10 milliliter container and put it into a 20 milliliter container, the gas will now be 20 milliliters. If you do that with a liquid, 10 milliliters of a liquid, and move it into a 20 milliliter container, it's still going to be 10 milliliters of the liquid. So for gases, they take up the volume of the container. And so if we have 4 particles of gases, and here we have 4 particles of gas. So the mass are the same, but the size of the container and the second example is bigger, and so the volume is bigger. Let's try a couple of CFUs. Remember, with each CFU, pause the video so you can see the answer. The images below depict the particle diagrams for two different samples of helium gas. Determine whether sample A has more, less, or the same mass, and more or less or the same volume. Then explain how you know. Pause the video now. Okay, here is the answer. So the correct answer is sample A has the same mass. If you count the number of particles, you see in both cases, they both have 8 particles, okay? All those dots there. So, and since we're looking at helium atoms, they both have 8 helium atoms. But sample A has a smaller volume because it's a smaller container. So A is in a smaller container, and so therefore the volume is smaller. Let's go to the next CFU. Take a moment to read the CFU, it's the same as before, and then pause the video to check your answer. Okay, the answer for this one is that sample A in this case has a larger mass because it has more particles. So if you count the number of particles here, there's still 8, but in sample B, there are only 5 particles. So A has a larger mass because it has more particles, but again, if you look at the size of the container sample A is smaller than sample B. So the volume of sample A is smaller. Okay, here's the last one. Again, it's the same question, so pause the video, and then after you pause it, get ready to check your answer. Okay, so sample A has a smaller mass because it has fewer, this should say fewer particles or less particles. So A has only 8 and B has 14, but the same volume. Both of the containers are the same size, so the volumes are the same. All right, now we're going to go into the next characteristics that we're going to describe with particle diagram, and that's temperature. Temperature is really a measure of how fast particles are moving. So when you have a higher temperature, something at a higher temperature, the particles in that sample are moving faster. And it's really hard to show movement in a particle diagram because a particle diagram is static. It's not like a video. It's just, you can't show movement in just one image, right? So what we can use is we can use these whooshies, whoosh, 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 which are just the lines behind, and the longer the line is, it's indicating that it's moving faster, therefore having a higher temperature. So if you look at the diagram on the left, they have longer whooshies, so they're moving faster, and that means they have a higher temperature, as compared to the one on the right, which is moving slower because they have shorter whooshies. So if they're moving slower, it's a lower temperature, slower, lower. Okay, let's try this next CFU. So temperature measures A, how many particles there are, B, how fast the particles are moving, C, how much space the particles are taking up, or D, how often and how hard the particles hit the wall of the container. Pause the video now, and then when you press play again, you can check out your answer. Okay, so the answer here is B. It's measuring how fast the particles are moving. That's what temperature measures. Let's take a look at what the other things are referring to. So how many particles there are, that refers to mass. How much space the particles are taking up, that's our volume. And the last one we actually haven't discussed yet, and that is pressure. So how often and how hard the particles hit the wall of the container is measured by the pressure. And that's where it's the last thing we're going to talk about, and that's pressure. So we define what pressure measures. Well, let's just break that down a little bit. So first of all, the harder the particles hit the wall of the container, the greater the pressure. And here we have an image showing gas particles inside of a container, and then these arrows are basically showing the movement of the gas particles. So if we take a look at this particle down here in the corner here, this particle is bouncing into the wall and then bouncing back off and then colliding with this one. And so that's what this arrow is showing. It's just showing the movement of this particle. So it's like pew, pew, right? So the harder the particle hits the wall, if this particle is hitting the wall pretty hard, then that means that you're going to have relatively high pressure here. The second thing that contributes to pressure is just not how hard the particles hit the wall, but also how often the particles hit the wall. So the more often a particle hits the wall, the greater the pressure. So if you have a lot of particles in a container, they're going to be hitting the wall a lot more than if you had fewer particles. And you can kind of think of that like kids running around in a room. So let's say you had 2 kids running around in a room. They're not going to hit the wall or bump into the wall. If they're running randomly, let's say. They're not going to bump into the wall as much as if you had 10 kids, right? The more kids you have, the more often a kid is going to hit into that wall. All right, let's try a couple of CFUs just to see, check your understanding for pressure. So the first one is, which sample has a higher pressure? You have sample A versus sample B, and explain. Here are a few hints here to help you figure that out. First off, which aspect of the 2 samples is different? So to compare the 2 samples, what do you notice about them? What's different about them? And does the thing that's different, or this aspect, does it affect how often or how hard the molecules hit the walls of the container? And if so, how does it affect it? Okay, so those are some hints of things you can think about, or self-questions you can ask yourself to help you navigate this question. Pause the video now, and then when you press play again, we'll reveal the answer. Okay, so in this case, the answer is sample B has a higher pressure because if you look at sample B, you notice that it has more particles than sample A. And the more particles you have, the more often they're going to hit the walls of the container. Thinking about kids running around in the room, right? So you're going to have particles hitting the walls more often, so you're going to have greater pressure. Let's try the next CFU. Again, which sample has a higher pressure? Again, you can use these hints, these 3 questions, so you can ask yourself to help you navigate this. Remember that pressure increases with how often the particle hits the wall and how hard it hits the wall. Pause the video now, and when you press play again, I'll reveal the answer. Okay, so the answer here is that sample A has a higher pressure because if you notice remember these whooshies are showing you how fast the particles are moving, and sample A is moving faster because it has larger whooshies, right? So the faster something is running around, the harder it's going to hit into a wall. You know, like if you just walk into a wall, it probably won't hurt you, but if you're running full speed, pew, that's going to hurt, right? So because you hit the wall harder, and the same thing happens with gas particles. So it's sample A has a higher pressure because the particles are moving faster, so they're going to hit the walls harder. That means with more force. Okay, thank you very much for taking time to watch this video. We will continue to discuss these particle diagrams throughout the unit and use it to help us navigate our understanding of gases. Have a quality day.